All right, you guys are going to learn today how to write the other type of ionic compounds, which are ternary ionic compounds. So yesterday and the day prior, I went over how to write binary ionic compounds with you guys. So binary means two. So up to this point, and I'm going to kind of use the pointer to show you guys, you have been taking one of these metals. So these are metals with definite charges, so those that are in the yellow, and combining them with one of these non-metals that are in the kind of teal, bluish aqua color over here. So, or the other type, where we have to use Roman numerals because you are using metals with variable ionic states. That is, they can have different charges, not just always the same charge like the ones in yellow. So you are pairing one of these up with one of these non-metals that are in this, again, this aqua kind of color. Now, what we're going to look at today is whenever these same metals, the ones in yellow and the ones in orange that we've been talking about, when they pair up with not just one of these 9, what we call monoatomic ions, because mono meaning one, they are just one non-metal atom, or one non-metal. We are going to see what happens when these metals, all right, any of these, the ones with variable charge or definite charge, combine with a group of nonmetals, which are known as polyatomic ions. So poly means many atoms. So over here, this is a list of the most common polyatomic ions. You guys don't have to memorize these. You will have a list provided to you to look at, all right? Now, I do want to zoom in for just a second. So these, where you see the just the negative charge, all right, so you see this BO3, not that one, but the C7H5O2 with the negative, that is understood 1. So that would be 1 negative, all right? And so any of these that you don't see like an actual number before the charge, it's understood to be 1. So right here, this is nitrate, which is 1 negative, and then nitrite, which is 1 negative also, all right? So these charges are important, okay, because these charges are what we are going to be using, just like we do with the nonmetals, these 9 over here, the 3 negative, 2 negative, 1 negative, we are going to be using the charges for these in order to write formulas and chemical names. Now, there's only one polyatomic ion that's positively charged, and that's ammonium. And so ammonium is a polyatomic ion that can actually act like a metal and lose valence electrons. So here's the deal. What is a polyatomic ion? It is a group of non-metal atoms. So right here, you see this NO3? That is a nitrogen. So I'm going to write this for you guys. So that is a nitrogen covalently bonded, which we haven't talked about yet, but you guys don't have to know all this. So it's a nitrogen and 3 oxygens sharing electrons, but they don't have enough to be stable. They actually need 1 more. And so that's where that 1 negative that's right there as a superscript comes into play. So you've got this polyatomic ion. So you've got this group of many atoms. So it's a group of non-metals. They're all non-metals. All right. So here's nitrogen and here's oxygen. So you've got a nitrogen, 3 oxygens acting like 1 ion. Okay. Acting like its own little unit. All right. So right here, so this is what is known as a nitrate ion. All right, its chemical formula is NO3, okay? So nitrate essentially acts like one of the halogens. It needs 1 more valence electron for that whole unit to be chemically stable. So that's how you're going to treat it. You're going to treat it like it is just an individual ion, because that's what's happening. These right here are stuck together sharing electrons, and they just want another electron. So let's do that. Let's give them another electron. So let's say that they bond with, and I'm just going to take one of the metals that has a definite charge. So I'm going to use aluminum since it's right here. And so let's say that we have aluminum, all right? Aluminum has a 3 positive charge. So aluminum has to lose 3 valence electrons in order to become chemically stable. So this is the same sort of thing we're seeing. Say if we had aluminum bonding with, say, chlorine, all right? Because chlorine has a 1 negative charge. So this group or unit, you don't touch it, you don't change it. You just say, okay, that's nitrate, and 3 oxygens, nitrogens and 3 oxygens. NO3 forever and always is a nitrate ion that is needing 1 more electron to become stable. So just like you would with the aluminum, you'd have to have 3 more chlorines, right, in order to make the compound overall chemically neutral. Same thing you got to do here, okay? In this instance, you're going to have 2 more of these nitrate ions. So now you don't have to write out this right here. I was just kind of showing you guys in when we get to Lewis dot structures with covalent bonds or covalent compounds, you'll see this more. But I just wanted to see you guys, let you guys see what that looks like as a working unit of nonmetal. So I'm going to actually get rid of it for right now, just so we can work with this just a little bit better. I don't want y'all to get expectations that you have to draw those. You don't. So you just go over here and you look at your list, you see nitrate, you say, okay, nitrate is NO3 according to the common polyatomic ions. I'm going to need 3 more of these, all right, in order for the charges to cancel. That is what we've been talking about with like these. In order for these to cancel out, I would need 3 more nitrates. Now, how do you write this in a formula? We know that the aluminum would be Al, that's 1 aluminum, and then 3 of these, so that would be Cl3. Now, polyatomic ions, when you have more than one of them, you have to protect them with parentheses, because like I said, you can't just change this 3 on it, right? So you can't change the subscripts. This right here, it is set. Like, you can't change it. You have to like write it as is. So you're going to say, okay, it takes 1 aluminum and then NO3. So you're going to put a parentheses around it when you need multiple ones, right? So, because I need 3 of those nitrate ions. So I'm going to say a 3 right here, okay? So that is how you would write the formula for aluminum nitrate, all right? You are balancing charges. So just like if we were going to take aluminum and put it with chlorine, which is just a binary ionic compound, right? Like we were doing the last couple of days. This is going to be aluminum with a group of nonmetals, right? They're known as polyatomic ions that are actually acting as if they are their own ion, all right? Because they are, all right? And they have a charge on them. So that unit, that entire group of 4 atoms needs 1 more electrons as a group. So that's why we have to have 3 of them in order to balance those charges or equal those charges and have an overall stable, neutral, net charge of 0 ionic compound, right? So something else that we've been doing the last couple of days is, or something you guys were working on, is writing the names. So when we were writing the names for our metals with a definite charge in one of these nonmetals, all you had to do is change the ending to IDE. So on your practice set yesterday, these were the ones on the very front page at the bottom. All right, so you're just changing the ending to IDE. So on that practice set, you guys had a list, like a way to drop the ending and changing it to IDE. So when it's a polyatomic ion, though, you do not change the name. You don't do any. All you do is say, as we were doing with the binary ionic compounds, you don't ever change the metal's name, period, anyways. So you just write aluminum, all right, and then you just write the name that you see over here. So you look up NO3 and you're like, oh, NO3, that's a nitrate ion. So look for your polyatomic ion, and then you just look it up on the list and go, oh, that's aluminum nitrate. So, of course, I'm going to have to show you how you do this with the metals that are in orange. That is, the ones that don't always have a definite charge. So, I'll have to show you that as well. So, let's take a look at that. Let's say you have the element iron. All right, so we're going to say iron, and we're going to pair iron with sulfur. All right, so we're going to say iron and sulfur are creating a compound. So, this is a binary ionic compound. So, if you have, let's say I give you the formula, all right, so iron and sulfur together. All right, so let's say that the formula is Fe2S3, all right? So, and let's now say we're going to take iron and we're going to combine it with one of these polyatomic ions. So you've got one of these with the multiple ionic states with one of your just typical nonmetals, all right, sulfur. And now we're going to take one of the metals with the multiple ionic states and I'm going to pair it up with one of the polyatomic ions. Okay, so I've paired up iron with a phosphate ion. So we're going to go over here and find phosphate, which is right here, PO4. So some of you might be like, well, I don't see any parentheses this time, so how do I know where it is? Well, here's the thing. There's a reason there's not parentheses around this right here, okay? And it's because there's only one of them. So some students are like, well, I'm not sure how do I find this polyatomic ion? How do I look at this and go, there's a polyatomic ion present? So here's the trick, okay? So you look up iron and you go, okay, iron's a metal, right? So we know this is an ionic compound immediately because there's a metal at the front. There's always a metal at the front in an ionic compound. So I then go, okay, here's my metal. Whoa, there's multiple elements behind it, right? So not just one, like over here, there's multiple elements. There's actually multiple non-metals, phosphorus and oxygen. If you have a metal followed by multiple, more than one non-metal, then it's a polyatomic ion, all right? So immediately, you're like, okay, everything else behind this metal, because there's more than one element, is on this list. So you go and you go, okay, so PO4, PO4, PO4. I go down here, I find PO4, all right? And I'm like, oh, that's phosphate. So that's going to help us out, right? So you find your polyatomic ion, which is phosphate. And so we are going to write the name for this. Now, keep in mind, we're dealing with these orange metals, all right? Or these metals with multiple ionic states. So when we get ready to write the name, we're going to have the metal, the ionic charge that we figure out, followed by the polyatomic ion's name. Like yesterday, we had iron, and then you've got to figure out your charge, and then you've got that non-metal's name changed with the suffix changed to IDE. So I'm going to start with the one that, based on what we did with the binary ionic compounds first, just because there's some familiarity there. So what we're going to do is we're going to go ahead and say, okay, this is iron, and then sulfur is going to come. So sulfur, remember, it's one of our 9 over here, and their ending changes to IDE. So don't forget, these guys over here, the ending changes to IDE, okay? So I'm going to go over here, and I'm going to change this iron sulfide, okay? All right, now we have to figure out what the charge is on the iron, all right? So like I said in the last video lesson, the biggest mistake is people want to go iron 2. They see the 2 after it, and it's like, it's 2. No, it's supposed to be a charge, so you have to take this formula and go, okay, this formula says that there's 2 iron ions and then 3 sulfur ions, right? Well, we do not know the charge on the iron ions, okay? But we do know the charge on sulfur. So sulfur is right here. It's one of our nonmetals, has a definite charge of 2 negatives. So 2 negative, 2 negative, 2 negative. That's 6 negative charges total. So that means I have to have 6 total positive charges. So that's 6 negative charges. That means I've got to have 6 total positive charges. So what type of ions are these? These are 3 positive. All right, so these are iron 3 ions. So you don't put a 6 right here. That's another thing students want to do. They're like, oh, that there's a 6 that goes here. No, it's not the total charges with like positive charges within the compound. It's the identity of the iron atoms that are in this compound. They are iron 3 ions. All right, they are iron atoms that lose 3 valence electrons to become stable. So that's what you're going to write is iron 3. We're going to write this as a Roman numeral 3, and that's how it would be, iron 3 sulfide. So we go over here to our iron that is now paired with phosphate, okay? So we want to know what version of iron is this. Is it iron 3? It could be iron 2 because that's another common, iron 2 positive is another common ionic state for the element iron. So we're going to go over here and we're going to say, okay, well, we don't know the charge on the iron yet, right? The one for this compound was 3, but this could be 2, it could be 3, all right? It could be a different charge. So we're going to go over here, and just like here where we had to use sulfur's charge to determine and kind of work backward, we've got to use the polyatomic ions charge because you guys will always have this list provided. So phosphate, PO4, and be careful with these sister ions. See how you've got a phosphate and a phosphite? Don't get those mixed up, all right? So we're going to go PO4, that's 3 negative. So if this is if I've got 1 phosphate and then 1 iron, this is 3 negative. All right, and there's only one of them. If there was more than 1 phosphate, then there would be like this and like a 2 on the outside, all right? But that's not the case, okay? So there's only 1 phosphate ion. So if the charge on the phosphate is 3 negative, this has to be 3 positive, all right? So this would be iron 3 phosphate. Right? And again, you don't change the ending, right? We're not going to change the ending of that polyatomic ion. We did have to figure out the charge, just like we did with the ones that we went over yesterday with binary ionic compounds. Okay, so I'm just going to do 4 more examples with you guys before I end this lesson. So when you look down here, a couple things I want you to notice. So when you attempt these, all of these different binary or ternary ionic compounds, you need to kind of have a game plan, kind of look over the chemicals before you just kind of jump right into it, because you need to know where you're going and what you're doing. Well, first of all, notice how these two have Roman numerals. That means they involve metals with variable or multiple ionic states. Now, the ones that don't are going to be here in the yellow, all right? Now, the other thing might be like, well, how do I know these are polyatomic ions, okay? Well, if you see an 8 or an ite, okay, I want you to notice that over here, not all of them, there's really, I think, only like 3 or 4, but most of them end with 8 or ite, okay? The exceptions would be like cyanide, azide, ammonium, hydroxide, which other ones? All right, so those are like, and then right here, a couple of this sulfide here, all right? But most of them end with 8, all right? ATE or ite, ITE, all right? So, and if you're ever in doubt, you're like, well, I don't know what element this is, right? If you look behind and go, I don't know what element this is, it's probably not an element. It's probably a polyatomic ion, okay? So these are in alphabetical order. You can just go to the list and find it. So this first one, chromium. Chromium is, again, going to be a metal with a variable charge. That's right here. That's chromium, is Cr. Now, chlorate. Chlorate is over here. Now, be careful with what I call these sister ions. You don't want to get confused with chlorite because they're different. So chlorite is right below it, okay? And you don't want to get confused. So make sure you're getting the right polyatomic ion. So chlorate is ClO3. It has a 1 negative charge. Now, according to this chemical name, chromium, this is chromium with a 2 positive charge. So here we are trying to write our ionic formula by equaling out these charges. So I'm going to need a whole nother chlorate ion in order to equal out these charges so that they cancel, all right? So the formula will be 1 chromium, and then because there's 2 of them, I'm going to have to protect the polyatomic ion with parentheses, and then there's 2 of them, all right? Now, our next one has magnesium, which is a metal with a definite ionic state of always 2 positive. So that's going to be magnesium, 2 positive. Now, nitrite, okay, so that's a polyatomic ion. Go over here. This is in alphabetical order. Here's nitrate. This is nitrite. All right, so nitrite is NO2 with a 1 negative charge. All right, so this is going to be, I'm going to need another nitrite ion, all right, so that these can cancel. So this would be magnesium, NO2, parentheses, 2, all right? So notice that we're never removing or changing the subscripts in any of these. You will never do that, okay? If you have more than one of them, then yes, you will have to put parentheses around them. And then the subscript of how many of those ions you total have. Now, sometimes you don't have multiple, so let's look at a one like that. So you've got potassium next, okay? So potassium is K, all right? So we've got potassium. It's one of those metals with a definite charge. Chromate, so chromate is a polyatomic ion. It's alphabetical. I go here and say, okay, chromate is CrO4, 2 negative. Oh, I thought this was one of them. I guess not. All right. So, well, yeah. All right, so potassium, potassium is 1 positive. We can see it's in group 1, it's 1 positive. All right, so in this case, we have potassium, which loses 1 valence electron, has a 1 positive charge, but the chromate ion needs to gain 2 more electrons, so that means we're going to need another potassium. All right, so how would we write this? All right, so we are going to go over here and we're going to say, okay, potassium, I've got 2 potassium ions, right? And then I only have 1 chromate. So here's a big mistake students make. A lot of students get in the habit of like putting these parentheses and they're like, oh, here it is, this is it. Do not do this, all right? Again, I'll say that again. Do not place parentheses. Do not place parentheses around the polyatomic ion when there is only 1. When there's only 1 present in the compound, okay? So this right here is not a thing, okay? You do not put parentheses around the polyatomic ion if there's only 1 in the compound, all right? So there's 2 potassiums, and of course you don't ever put parentheses around just individual ions, all right? So K2CrO4 would be our compound's formula. All right, so our last one, we've got another one of these metals with multiple ionic states. So we're going to take the nickel. All right, this means 3 positive, right? Just like this meant 2 positive. So nickel, which is Ni, has a 3 positive charge. Right, I don't want to get too close to the bottom of the screen, so make sure you guys can see. So you've got nickel with a 3 positive charge. Now hydroxide, this is probably one of the most highly polyatomic ions. That people's like, what element is that? Hydroxide's not an element, all right? It's a polyatomic ion. So like I said, if you ever have a hard time finding it on the table, it's probably not an element. It is a group of elements. It's a polyatomic ion. So hydroxide is actually OH with a 1 negative charge, all right? So I've got nickel that has to lose 3 valence electrons, but hydroxide only wants 1, so we're going to need 3 of these in order for them to cancel out, all right? So this is going to be 1 nickel, right? And then 3 hydroxide ions, so this is going to be 3 of these, all right? So do not do this. This is such a common mistake. People put a 3 right here, all right? Do not do that. That is an oxygen, 1 oxygen, and 3 hydrogens. You want 3 of this entire thing. So you have to put a parentheses around the OH because that is the hydroxide ion. And so that would be nickel 3 hydroxide's formula. All right, so you guys are going to get some practice with this that you'll need to complete after the closure of this video lesson.